Hello, welcome to CSC 8025, Computer and Network Security. My name is Brady Chen. I'm from Department of Computer Science at Fitchburg State University. So the course consists of many modules which cover the fundamentals of number theory, authentication and encryption and decryption technologies, as well as some of the well-known security-related topics. And it also covers some well-known encryption and decryption algorithms widely used in industries. Okay, Module 2, Classical Encryption Techniques. Now, the classical encryption techniques can be traced all the way back to the Roman Empire. Now, there are two basic techniques. One is the substitution, and the other one is the transposition. And we will talk about these two later. Okay. The earliest known use of a substitution cipher was by Julius Caesar. Okay. So many of the ciphers used during the World War II are also regarded as the classical encryption techniques. Okay, we will divide Module 2 into two parts, Part A and Part B. Now, in Part A, we'll present an overview of the main concepts of symmetric cryptography. Now, remember, in the previous module, we discussed three types of algorithms: non-key, single key, and the two-key encryption algorithms. Now, symmetric encryption is a single key encryption. It is also referred to as a conventional encryption. Okay. Now, the symmetric encryption was the only type of encryption used prior to the development of the public key encryption. Okay, public key encryption is also known as the two-key encryption algorithm. It was developed in 1970s. Okay, and then we will also explain the difference between cryptanalysis and the brute force attack. Now, to break the encrypted message, an attacker will also use some techniques. Okay. Now, brute force attack is to try all the encryption keys. Now, if the number of keys for the cipher is limited, so in that case, you try all the possible keys and try to break the message. Okay, and then we will actually explain the difference between the general cryptanalysis and the brute force attack. Okay, now also we will discuss and understand the operation of monoalphabetical substitution cipher. Okay, this is one of the techniques that which extends the classical Caesar cipher. Okay. Now, in this slide, we're going to introduce and discuss the terminologies and definitions used in the encryption and decryption algorithm. Okay, so the first one is the plain text. A plain text is the original message, which is the message before the encryption. Okay, and then the ciphertext refers to the coded message. Okay. So typically, a ciphertext is unintelligible. Okay. Now, this third terminology we're going to talk about is the enciphering or encryption. Okay. Now, the enciphering and encryption is the process of converting from plain text to ciphertext. Okay. Now, a big part of this course is to discuss various different algorithms, enciphering and encryption algorithm. Okay, and deciphering and decryption is the opposite. It's basically is used to restore the plain text from ciphertext. Okay. Now, cryptography, okay, is the term basically refer to the area of study of many schemes used for encryption. Now, cryptography is one branch of mathematics. And then we can talk about cryptographic system or cipher. Okay, that's the scheme, or many times it's the algorithm. Okay. Now, cryptanalysis. So cryptanalysis is a technique used for deciphering a message without any knowledge of the enciphering details. Okay. Now, typically, it's different from the encryption and decryption, because when you do the decryption, you have the key, and you use the key to convert the ciphertext into the plain text. Just restore the plain text from the ciphertext. Now, cryptanalysis basically uses the techniques to break the ciphertext messages, without any knowledge of the enciphering details. So typically, it's illegal, or it's the action of attacking a system, attacking the encryption algorithm. Okay. Now, so the cryptology is the areas of the cryptography and the cryptanalysis. So it's basically combine the cryptography and the cryptanalysis, and then we use one terminology which is called cryptology. Okay, now here's the symmetric cipher model. Now we're going to use this diagram to illustrate the symmetric cipher model. Now in this diagram, the first thing we need to look at is the data block. Data block is also the plain text, which is the original message. Okay. Now you can actually send the plain text to the cloud and then to the destination. Now the problem with this is the cloud, the internet, is not secure. So everybody can play in this cloud. So it's a sandbox. So whoever intercepts the message X can read the message, whether they are authorized or unauthorized. Everybody can read it. So that's not good. Okay. So here, in this symmetric cipher model, we're going to use the algorithm called the encryption algorithm. Okay. Now the encryption algorithm is going to take the plain text X and then mixed with another message, a short message K, which is known as the key. Okay. It's a secret, it's a private. So encryption algorithm is going to take plain text and mix it with the key. It will generate a new message, Y. Okay. Y is the ciphertext or encrypted block. So Y is unintelligible. So when you send this message Y to the cloud, hopefully it's safe, because whoever actually intercepts the message cannot read it. Okay. So, however, when the receiver receives this message Y, then the receiver can use the algorithm called the decryption algorithm. Okay, and mixed with the key. Remember, it's the same key used for encrypted message. Okay, and then hopefully we're going to generate the message, which is the original message X. Okay, so here we use the encryption algorithm and a decryption algorithm. Now let's assume that we use the E to represent the encryption algorithm, a D to represent decryption algorithm. So we can interpret the E as a math formula, right? Now this formula is going to take two parameters. One is K, which is the encryption key, and the other one is the plain text. Okay, so two parameters, K and X, and this formula going to generate the value y, which is the ciphertext. Okay. And on the decryption side, okay, we use the formula D and also the key, which is the same key, and the ciphertext. And hopefully this is going to restore the ciphertext, the plain text from the ciphertext. Okay. So that's the typical symmetric cipher model. Okay, to make the symmetric cipher model work, now there are two requirements for secure use of the conventional encryption or the symmetric encryption. One, we should have a strong encryption algorithm. Okay, now if you look at the model, the diagram, so we should have a strong encryption and decryption algorithms. Okay, now we're going to talk about this. What does a strong encryption algorithm mean? Okay, later. Two, the sender and the receiver must have obtained a copy of the secret key in a secure fashion and must keep the key secure. So the key, how to maintain and make the key secure. Okay, that's very important. Now let's first talk about the first one, the strong encryption algorithm. What does a strong encryption algorithm mean? Now, at a minimum, we would like the algorithm to be such that an opponent or an attacker who knows the algorithm, okay, and has access to one or more ciphertext would be unable to decipher the ciphertext or figure out the key. Now, there are two meanings in this. One, so we cannot assume that the opponent or the attacker doesn't know the algorithm. Okay, we have to assume that they know the algorithm. So the algorithm should be known. In general. And also, they should have one or more ciphertext. Because the ciphertext is also sent through the cloud, or internet. So the internet, for internet, everybody can intercept your ciphertext. Now the security of the message is not rely on to maintain a secret channel for the ciphertext. Security is actually maintained by, make the ciphertext strong so they cannot, break it. Okay, so we have to make these two assumptions. Okay, if the opponent or attack has these two, satisfy these two conditions, they still cannot, break the message, and then we can say the encryption algorithm is secure. Okay. Now the second part is related to the maintenance of the secret key, because you have two conditions. One, both sender and receiver are going to share the key. So now, how can you actually securely deliver the key from sender to receiver or from receiver to the sender? And the other thing is that once the key is delivered, how can we maintain the key secure, to keep the key secure? So these two are very important, okay, to make the symmetric cipher model work. It sounds simple, but it's not really that simple. Okay, so here we basically summarize the symmetrical encryption scheme as in this diagram. Okay, it's pretty much the same as the previous one, but then we have a message, that's a plain text, an encryption algorithm, decryption algorithm, and then we have a key Now we need to build a secure channel to share the key between the sender and the receiver. Okay, so you have to do with a secured channel. Okay, so also we have to make sure, the opponent or attacker, okay, or we call it crypto analyst, okay, so they may actually, intercept the message. Why, right? Okay, so somehow they should not be able to break this message in two senses. One is, they should not be able to break the message, okay, without a key. Now the other ones, they should not be able to get the key, because getting the key is the same as, it's almost the same as breaking the message, because once you got a key, you can easily, use the decryption algorithm to restore the original message. Because remember, both the encryption and decryption algorithms are known. We have to assume that these decryption algorithms are publicly known. Okay, so let's talk about the implementation details of a cryptographic system. Now, cryptographic systems can be characterized along three independent dimensions. Okay, so we're going to talk about these cryptographic systems from three aspects. Now, the first one is the type of operations used for transforming plaintext to ciphertext. Okay, now there are in general two types of operations. One is the substitution. Okay, the other one is the transposition. Okay, now, so in substitution, each element in the plaintext, whether this element is like a binary bit or a character, a letter, or a group of bits or letters, is mapped into another element. Okay, so that's the substitution. Now, in transposition, the elements in the plaintext are rearranged. Okay, so basically we reshuffle the original message. Okay, by reorganize the characters, and on the decryption side, we basically just actually inverse this process and restore the original message, the ciphertext into the original message. Now, second aspect is the number of keys used. We already talked about a symmetric, single key, secret key, and conventional encryption. Okay, but for the symmetrical system, it's always the single key, and that single key is a secret key. Okay, we have talked about this in the earlier slides. Now, for the asymmetric, typically we use two keys, or sometimes we call it public key encryption, in which there are two keys. One is called the public key, the other one is called the private key. So we either going to encrypt the plaintext using the public key and decrypt it using the private key, or vice versa. We encrypt it using private key and then decrypt it using the public key. Okay. Now, the third dimension, okay, or the last aspect of the cryptographic systems is the way in which the plaintext is processed. There are two ways. Okay, block cipher and a string cipher. A block cipher processes the import one block of elements at a time. So we divide the original message into blocks of the same size, typically. And then each block produces an output block for each import block. Okay, so that's block cipher. A string cipher processes the import elements continuously. Okay, so producing output one element at a time as it goes along. Okay. Okay, so let's talk about the cryptanalysis and the brute force attack. Now, in cryptanalysis, attack relies on the nature of the algorithm, plus some knowledge of the general characteristics of the plain text. Okay, now you can think about these as like an algorithm as a math function. Okay, let's say it's a math function E. That's the encryption algorithm. So now people apply this function, with some of the parameters like a key and the plain text X. Then we calculate the value, okay, which is the ciphertext. Now in cryptanalysis, the attacker basically study the algorithm or study the function and try to find the inverse function. So using the math knowledge, so we find the inverse function, e to the minus 1. And then the inverse function is going to use the key and the ciphertext, so hopefully we can restore the original message. Okay. So attack exploits the characteristics of the algorithm and to attempt to deduce the specific plain text or deduce the key being used. Okay. Now, let's talk about the brute force attack. It's a specific type of attack. Now, in brute force attack, attacker tries every possible key on a piece of ciphertext, okay, until an intelligible translation into the plain text is obtained. Now, there's one condition. When you use the brute force attack, you have to attack an algorithm with a limited number of keys. Okay, so for example, if the encryption algorithm use only 100 keys, now then with a piece of ciphertext, okay, and then you can try all 100 different keys. You can try the first key and combine the first key, key 1, with the ciphertext and try to generate a message, right? I call it X1. Okay. Now then you use the ciphertext and use key 2 and to generate another message, X2. Because the number of keys are limited, so you only actually requires 100, tries. So let's say we have 100 keys, and then the last key is key 100. With the ciphertext, we generate X100. And then we study each of the, decrypted message using different keys. Now, if X1 doesn't make sense, X2 doesn't make sense, and suddenly we find out a particular one, like XK, which is intelligible. Then we know, this is the key. Okay, this is the key used, and then we can use the key to decrypt any other ciphertext. So on average, half of all possible keys must be tried to achieve the success based on, this is based on the statisticals. If we have, for example, 100 keys, the total number of keys is 100, then hopefully, statistically, you can actually get the keys by trying half of these total keys. Okay. Okay, let's summarize the types of attacks on encrypted messages. Now, in this table, we list the type of attacks on the left, and we also provide some of the known information to the cryptanalyst, because the goal is to break the message, right? So we have a type of ciphertext. The goal is to break this ciphertext to get the plain text. So now in the different scenario, so the cryptanalyst has various different information. Okay. Now The most difficult case is the first case, the ciphertext only. Okay, so the cryptanalyst has no any other additional information besides the encryption algorithm and the ciphertext. So that means the only known information is the encryption algorithm. Remember, the algorithm is always known. We always assume that algorithm is known to the public. And also the ciphertext. Of course, if you want to decrypt the message, you have to have at least a piece of a sample of ciphertext, right? At least this. So that's the only two, known information. That's the toughest one. However, in many scenarios, the cryptanalyst knows these two information plus some additional information. Okay. Now the next one is a non-plain text. So in this case, the cryptanalyst knows the first two, encryption algorithm and the ciphertext, plus one or more plain text ciphertext pair formed with the secret key. Okay. You may wonder, how does a cryptanalyst know these, plain text ciphertext pairs? Now, in certain case, that's possible. Okay. Now, let me give you an example. Suppose if I want to actually attack some of the, the company, and I try to get the information from this company. Okay, I know I can get most of the ciphertext from this company, organization, right? I can get the ciphertext. Okay, now this could be like a typical company document. Okay, now of course you don't know the ciphertext. You don't know what's the meaning of the ciphertext. However, if the attack actually once worked in the company, the attack may have access to some of the documents, and then the attacker found out, for most of the document in this company, they have certain kind of format. For example, the first page is the company logo and some of the statement. And then start from page 3, and then that's a detailed information. So once you apply these, now once you get the ciphertext, now the attacker know, or at least the first piece of information is encrypted from here. Now, because we know that the first couple of pages, it's basically some kind of a company legal statement, logo, and all this information. So it's for every actually document, they always start with these 2 pages. So in that case, you actually have the plain text, at least for these 2 pages, and then you grab the ciphertext. This first actually 2 pages of ciphertext was encrypted from this plain text. So now you have the plain text ciphertext pair, right? This is going to actually help you, to crack these message. Okay. Now, third case is a chosen plain text. So let's actually say the first 2 always available, for every type of attack. Now the chosen plain text is that the plain text message chosen by a cryptanalyst together with its corresponding ciphertext generated with the secret key. If the attacker has the opportunity to choose its own plain text and use the encryption algorithm to generate the ciphertext, so now you have a chosen plain text with its corresponding ciphertext. So that's another situation. Okay. Now the chosen ciphertext. So in this case, besides the first two conditions, now the ciphertext chosen by the cryptanalyst together with its corresponding deciphered plain text generated with a secret key. So if the attack has that information. Okay. Now the last case is the attacker has both the information about the chosen plain text and the chosen ciphertext. So the attacker has more information available. So this is going to make it easier to crack the messages than the very first case. That's the most difficult case. That's the most difficult. Now I'm not going to say it's very easy, but at least it's easier than the first case. Now let's talk about encryption scheme security. Now, in general, there are two security types. One is called unconditionally secure. Okay, what is unconditionally secure? So, in unconditionally secure, no matter how much time an opponent has, it is impossible for him or her to decrypt the ciphertext simply because the required information is not there. Okay, so unless you have some piece of information about a key, otherwise, it's impossible to break it. Now the other one is the computationally secure. So there are two meanings of this. One is the cost of breaking the cipher exceeds the value of the encrypted information. Okay, that's one. The other one is about the timing. So the time required to break the cipher exceeds the useful lifetime of the information. Okay, for example, if a person wants to attack your bank account, or crack your information. Now, so this guy just spent a lot of time working on the encryption algorithm and eventually crack the account, and he or she got $10,000. But the cost he or she applied to crack your account is more than $10,000. So that means that the cost of breaking the account is more than the value of the account itself. Now in that case, mostly people are not going to try it. They just going to give up, because that's one aspect of the computationally secure. The other one is the time required to break the cipher exceeds the useful lifetime of the information. For example, let's say if I use the brute force attack. Remember, the brute force attack is based on the number of keys, right? You can with a ciphertext, you basically try all the possible keys and eventually find out which key is the right key, so they can eventually break the message. Now, if someone basically used the most advanced technology, used the most powerful PC, and they used the algorithm to try all the possible keys, okay? Now, the computer actually takes about, in theory, going to take about 100 years to complete all the keys. You will try the very first key to the maximum number of keys, and it's gonna take like 100 years to eventually break your message. Okay, now that's not realistic, right? So this is also the computationally secure. So that means if people are gonna say, oh, I want to try to break the message, I use brute force attack, but the attack itself is going to take like 100 years. Then that's computationally secure. Okay, so let's talk a little bit more about the brute force attack. Okay, so as we mentioned earlier, the brute force attack involves trying every possible keys until an intelligible translation of the ciphertext into the plain text is obtained. Okay. Now the key is you stop it until the intelligible translations of the ciphertext into the plaintext is obtained. Okay. Now the challenge is, number one, if the number of keys is huge, then the time to perform the brute force attack is going to be very long. So on average, half of the possible keys must be tried to achieve success. Okay. Now that's not all, because it seems like, oh yeah, we can try all the possible keys, and then we find out an intelligible translation of the ciphertext into the plaintext is obtained. Now, when you actually do this, it's more difficult. It's more actually complicated than it is. Now, to supplement the brute force attack, a certain degree of knowledge about the expected plaintext is needed. Okay, what does that mean? Okay, so this means that the analyst must be able to recognize the plaintext as a plaintext. Now that sounds kind of stupid, right? Why recognize plaintext as plaintext? Now the reason we mention this is because the plaintext could be written in English. Now that's probably the easiest case. So once you have a plaintext as English, then you use, for example, Caesar cipher or mono alphabetical ciphers. So you can actually encrypt it into a different ciphertext, and then you can that you try all the possible keys, and then that one of the key gonna generate the message, which is the plaintext, and which is the English. So now this is the key used to encrypt the message, because I can read the English, because I successfully break this message, the ciphertext, because the message is intelligible. Now, what about if the original message is French or German? Okay, so now they use the encryption algorithm and use the key to encrypt the message and get the ciphertext. Now, if you don't know how to read French or German, even the plaintext has been obtained, you still don't know that's the plaintext. Okay, that's the problem. So now, in most cases, when people use these encryption algorithms, they're not going to simply use the algorithm to encrypt the English language, English message, right? So they're going to do a little bit more. For example, if the text message, like English sentence, has been compressed using some kind of compression technique, which is not readable, and then using the compressed message like a zip or other kind of like a simple compressed compression, then you got the compressed message, and then you actually apply the encryption algorithm. Okay, so now you got the ciphertext. Now when you try all the using the brute force attack and try all the keys, and then you got a list of the encrypted messages, but none of these are intelligible, because even the correct plaintext is not readable, because it's compressed message, unless you have some expertise in your team knows the characteristics of compressed message, and then they can just guess, oh, that looks like a compressed message of English. Okay. Now, to make things even worse, so some of the data are numeric files, and then these numeric files has been it's like a sequence of numbers, and that numerical file has been compressed. So that the problem becomes even more difficult to automate. Okay, so that's the problem with brute force attack. It's not that easy because people don't simply use the brute force attack, encrypt the message using English language or any language that you can easily recognize. They may use some kind of trick to convert the the original message into a plain text that is not easy to recognize. Okay, that's the challenge. So the term strong encryption refers to the encryption schemes that make it impractically difficult for unauthorized users, unauthorized persons, or systems to gain access to the plain text that has been encrypted. Okay, now there's a requirement for strong encryption to protect the data for users, such as like a security managers, organization, executives. Now many organizations have the different security levels. However, the term strong encryption is an imprecise one. It's actually it's a general term. Okay. Now here are the properties that make an encryption algorithm strong. Okay. Now I'm not going to spend much time discuss about these because this is not the main focus for this course. One of the properties is that the appropriate choice of a cryptographic algorithm. We have to choose the algorithm very carefully to make the encryption strong. Now the second one is use a sufficiently long key length. So now this is actually important because most of the encryption algorithms use binary sequence to represent the key. Okay. Now if you use a very long sequence, for example, we use 32 bits, binary bits, okay, to represent the key. Now, if you know the binary numeric systems, you know that how many different numbers you can represent using 32 bits. Okay, the answer is 2 to the 32. So you can use 32 bits to represent 2 to the 32 different numbers. Now, each number going to represent a key. So that means you have 2 to the 32 different keys. Now, if you use brute force attack, then you have to try 2 to the 32 different keys. That's a very big number. Now, in modern days, even 2 to the 32 is not big enough, so it's still not secure to the brute force attack. But now people can increase the key length from 32 to 64 bits. Now with 64 bits, it can represent 2 to the 64 different keys. Okay. And then the other properties include appropriate choice of protocols, well-engineered implementations, absence of deliberately introduced hidden flaws. These are all the properties related to strong encryption. Okay. So remember, there are two types of operations. One is the substitution. The other one is the transposition. Now, let's talk about the substitution technique. Okay. Substitution techniques is one in which the letters of plain text are replaced by other letters or by numbers or symbols. Okay. Now, in most of the modern encryption algorithm, the plain text is viewed as a sequence of bits, the binary bits. And then the substitution involves replacing the plain text bit patterns with cipher text bit patterns. So you replace one sequence of binary numbers with another sequence of binary numbers. Okay. Now let's talk about the Caesar cipher. Now Caesar cipher is the simplest and earliest known use of a substitution cipher. Now, according to historical records, that Julius Caesar is credited with using a cipher method now known as the Caesar cipher. Okay, the Caesar cipher involves replacing each letter of the alphabet with the letter standing 3 places further down the alphabet. Okay, of course the Caesar did not use English, but let's say we use the example of English language. Let's say we have alphabet like A, B, C, D, E, F, all the way to X, Y, Z, right? So now we're going to replace A. If the A is in the plain text, we're going to replace the A with the letter standing 3 places further down, which is D, right? 1, 2, 3. Okay, so A will be mapped to D. Now B will be mapped to E. C will map to F. Okay. Now, if for the value of, for the letter X, so we can, which value X can map to? Let's say the next one is Y, 2 is Z, and there's no actually, character after Z. So basically we're going to circle around back to A. So X going to map to A, Y going to map to B, and Z going to map to C. So we basically use this circular way. So that's the Caesar cipher. It's pretty simple. Okay. So for example, if we have a message, the plain text message, say, meet me after the toga party. Okay, so you can send this message out, but this is a plain text, so everyone can read it. Now we do a little bit of trick with the Caesar cipher, so we can actually, encode each of the letter with the letter standing 3 places further down. So M gonna be mapped to P, and E gonna be mapped to H, E gonna map to H, T map to Y. So we can actually map each of the letter to its corresponding letter in the ciphertext. So then the ciphertext for the original plain text becomes this. Now in the ancient time, when one of the army want to send a message to, in the battlefield, even this message was captured by enemy. Hopefully, it's not easy to, to decode the message, right? But the encryption is very simple. It just actually shifted the letters. Now here we're going to talk a little bit about the Caesar cipher algorithm. So here are the steps. Okay. Now first we're going to define the transformation. As we mentioned, that the Caesar cipher basically replaced the letter with the letter, standing 3 places down. Okay. So we build that table, right? Okay. Now in this case, what is the key for the Caesar cipher? Okay. Now the key, because we shift 3 positions down, so the key is actually 3. Okay. Now you can directly apply the Caesar cipher to the English characters, but we can actually provide some kind of mathematical formula to calculate the ciphertext using numbers. Now first, before we do this, we need to create the mapping between English letters to numbers. So we can map A to 0, B to 1, and the last character Z to 25. Okay. So now we use we encode English language using the digitals, using the decimal numbers. Okay. So now what's the advantage of using numbers? Because we can use the math formula to operate on numbers. Okay, so the algorithm can be, the Caesar-Salford algorithm can be expressed using the math formula. Okay, so we can say, okay, E is the encryption algorithm, and then the key, as we mentioned, the key is 3, right? And the P is the plain text. Now, the P could be 0, 1, 2, or 25, right? So now the encryption can be written as this P plus 3, because whatever the value of P, okay, we plus the number 3 to increase the number by 3. Because remember, in this table, if the current value P is 11, so then what's the P plus 3? P plus 3 is 14. So that means the plain text 11 going to be mapped to 14 under this, algorithm. However, we also put a modular operation, with 26. Why we're not going to put the modular operation? If you know modular operation, we know that the reason we're going to put the modular operation is because if P is like a 24, okay, now what's the ciphertext? So we're going to use P plus 3, which is 27. But now if we look at this table, 27 is not there, because the number is from 0 to 25, but 27 is not. However, because the table is built with a circular way, if it's 27, if we use the modular operation, we can divide 27, okay? So we can divide 27 by 26, okay? So once we divide 27 by 26, and then we get the quotient, which is 1, and then we get the remainder, okay? So the remainder going to be the answer. So 27 modulo 26 is 1. Now that's the plain text, okay? So that means the number 24 will be mapped to 1, okay, in a circular way. So in general, the shift can be maybe of any amount, so that the general Caesar algorithm is going to be EKP. Now instead of 3, we replace with K, so that the algorithm is going to be P plus K. Okay, K is the number. Okay, so if we choose K equals 10, that means each character going to be replaced by a character like 10 positions down. Okay, but we still need to use the modular operation. It's mod 26. Okay, if it's end of the list, then we're going to circle around and go from the beginning. Now, so in this case, you can use the K3, right? Now, if the K is 0, that means we don't actually change anything. A maps to A, B maps to B, or 0 maps to 0, and 25 maps to 25. So K equals 0 is actually almost like we are not doing encryption at all. Now K equals 1, that we shift 1 position down. K equals 2, we shift 2 positions down, right? Now, but once we reach the end of the list, then we circle around. Now, what about if K is 26? If K is 26, now with the modular operation, we will find out if K is 26, then it's almost like we're not doing shifting at all. For example, let's take a look at the example. Like if K is 26, okay, now the plain text is 3. So now what is the answer? Encryption. P plus K is 3 plus 26, which is 29. Now if we actually use the modular 26, so 29 modular 26, now we got a 3. Okay, so the original text is P is 3, but the encrypted message is also 3. So that means using Caesar cipher, we can choose k equals 1, 2, 3, and all the way to 29 or 25. But if we reach 26, it goes around again. So it's almost like we're not encrypted at all. Okay. Or if we also include 0, then the number of keys could be from 0 to 25. So the total number of key is 26. Okay. What does that mean? So that means, you can easily apply the brute force attack for the Caesar cipher. You can try for the cipher text. You can try key equals 1, or key equals 0, 1, 2, 3, 4, and all the way to 29. And then one of the number must be the key. Okay. Now the decryption is pretty straightforward. If encryption is actually choose the letter like a k positions down, and the decryption should choose the number that is a k positions, up, right? We move the opposite way. Okay, so that's the reason the decryption algorithm is going to be like a C minus k. C is the ciphertext, and also we use the modular 26 because it's we have to do the circular thing. Okay, so let's take a look at an example of brute force cryptanalysis of Caesar cipher. Okay, now this is actually the example in the previous slide. Okay, so the ciphertext is this. Start with PHHW, blah blah blah. Then, since the Caesar cipher has only 25 different keys. Okay. So we can try these by using the table on the right, which is that the chart can be found also on page 71 in the textbook. Okay. So we can try to decrypt the message using different keys. Key equals 1, key equals 2, da 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 da. Now let's say when we do the key equals 1, then we're going to shift each of the characters in the ciphertext to the left. Okay, one position. Okay, because this is decryption, so we're not going to shift it to the right, but shift it to the left, one position. So P will be replaced by O, which is one positions on the left. H will be replaced by G, V. Okay, W will be replaced with B. So then with the key equals 1, we try to decrypt the message, and that's the message we got. Well, doesn't look like it's a plain text, right? Because it's still unintelligible. And then we actually choose the key equals 2, so we basically shift the original message to the left 2 positions, or we can shift the original message to the one position to the left with the above message, right? So anyway, we got this. Okay, and then with key equals 3, we shift it to the left 3 positions. Okay, so then we got this message. Okay, and then we can continue, but in this case most likely we can stop because we know that this message is readable, so we can actually understand what's the meaning. So meet me after the toga party. Okay, now if we continue to do this for the remaining keys, and we'll find out none of these are actually readable. So that's the one. Now, sounds like it's so simple, and the original key is 3, right? And we actually decrypt the message. But again, as we mentioned earlier, it was because the original message was English. So then we try different keys, and we know the plain text should be in English, so we can understand it very easily. But if the original message was not English, then it's not that simple to do that. So that's the example of the brute force attack. Okay, so here let's talk about the challenges with the brute force attacks. Okay, now in the previous example, we did the brute force cryptanalysis, and we easily find the original plain text. That was a kind of a very special example because the plain text was written in English. Okay, so now the challenges with the brute force attack is that now in cryptanalysis we should always assume that the algorithms are known. So okay, so in this case with the brute force attack, we should be able to know the algorithm. If the algorithm is a Caesar cipher, then we know the decryption is relatively simple because the number of keys is limited. Now, in this case, with English language, we only have 26 different characters. So the number of key is about 25. Okay. Now, what generally makes the brute force cryptanalysis impractical is the use of an algorithm that employs a larger number of keys. Now, for Caesar cipher, it's very different story because the number of keys is limited. But now, if we use any algorithm with a larger number of keys, then the brute force cryptanalysis is going to be very challenging. Now, one of the examples is the triple DES. Now, DES is the algorithm that is actually released by NIST, and so it's actually like a very standard encryption-decryption algorithm. Now, triple algorithm is actually applied DES 3 times. This is due to the fact that the DES is actually kind of less secure due to the development of the computer actual technology. Okay, so the computer becomes faster and faster, and make the brute force cryptanalysis, easier and easier. Okay, so the triple DES algorithm makes use of a 168-bit key. Okay, remember, when the key is actually used binary numbers. Now, then the number of keys you can represent is depend on the number of bits. Okay. Now, we mentioned that with 32-bit keys, then you can actually use technically 2 to the 32 number of keys. Okay, if the key length is 32-bit. But now using triple DES, we use the key of 168 bits. Okay, so this is going to give you the key space of 2 to the 168, or if we calculate this number out, it's like a 3.7 times 10 to the 50 possible keys. Okay, that's a huge number. Okay, later on we can give you an example of how difficult that we can crack the keys using brute force attack if the key length is extremely big. Okay, and the other thing we also mentioned earlier that if the language of the plain text is unknown, then the plain text output may not be recognizable. Okay, so we mentioned again that in the previous example the plain text was English, so then we know it's easy, right? But if the plain text was French or even Chinese, Japanese, Koreans, wow, that's going to be very challenging, because even though you get the right plain text, but it's still not recognizable, if unless you know the Chinese or Korean. Okay. So the import also may be abbreviated or compressed in some fashion if you use some kind of compression, like a zip file, compressed file with zip, or using some kind of compressed software. And then this making recognition difficult. Okay. Now, in the textbook, if you look at the figure 3.4, and then you can see what the compressed text can look like using zip. Okay. So also we can show this in the next slide. And also, if the file is then encrypted with a simple substitution cipher, then the plain text may not be recognizable when it is uncovered in the brute force attack and cryptanalysis. So basically, you combine two encryption algorithms. One using a very simple, like a substitution algorithm, like a Caesar cipher. We switch the original, text, and then we apply like a DES. So then, you use the brute force attack, a cryptanalysis to break the DES, like a triple DES, and you got a whole bunch of messages, and then which one is the plain text? Because it's already actually used the Caesar cipher to encrypt the original plain text to the cipher text. So now you use the triple DES to encrypt the cipher text, which was generated by the Caesar cipher. So you use the encryption twice, even though the first one is very simple, but it's already caused a lot of challenge. Okay, so this is the example, of a compressed file, a text file. It's actually original is a text file, like an English character. Then after the compression, using the zip software, then you will find that the message looks like this. Okay. Now, if someone, after you compress the original text message into a zip file like this, and then you apply the encryption algorithm using the zip file as the plain text, and then you encrypt it using zip file as a plain text, and then generate the cipher text. Okay, so now you apply the brute force attack with the algorithm, and you generate all these original message, and then even though you one of the key actually, the right key actually, decrypt the message as this, and you still don't know, you still have no idea, oh, this is already the plain text. This is the problem, the challenge. Okay, so we now know that the Caesar cipher involves replacing each letter of the alphabet with the letter shifted a fixed amount further down the alphabet. So the shift could be 3, 4, so which generate a different algorithm. Now, Caesar cipher is not secure, because with a brute force attack, you just need to try only 25 different keys. Okay, so we see the example, right? Now, let's extend the Caesar cipher to, the monoalphabetical cipher. So, monoalphabetical cipher is an extension of Caesar cipher. In this case, we're going to map each of the character to any characters in the set of alphabet. Now, for example, the first one, this is the one we used in the Caesar cipher with key equals 3, right? K equals 3. So for example, we map A to the D, which is shifted to the right 3 positions. Now B maps to E, C maps to F. Okay. Now in this mapping, each character in the plain text maps to the letters 3 positions to the right. Okay, that's fixed. But not the monoalphabetical. The monoalphabetical can map A to any character in the list. A could map to A, could map to B, could map to C, or any 26 letters. And also, once the map of A is selected, then you can map B to any remaining alphabet. Now, for example, if A already mapped to C, for example, A has been mapped to C, then B can map to any letters, okay, other than C. So B can map to A, can map to B, could map to C, D, but not to C, because C is already mapped by A. Now we keep going this way, then once we complete the mapping of all the letters, then we successfully define a key. Now with monoalphabetical, how many keys we can have? Okay, let's take a look at the next slide. Now before we talk about the monoalphabetical ciphers further, we first need to introduce a term called a permutation. Now, a permutation of a finite set of elements S is an ordered sequence of all the elements of S, with each element appearing exactly once. Okay, now in order to discuss the permutation, we first need to introduce a set of elements S. Let's say we have a settlement of element of 4 or 3. Let's say 3 elements A, B, C. Okay. Now, what's a permutation of S? It's an ordered sequence of all the elements of S. Okay. So let's say how many sequences we can discuss with 3 elements, like in this case S. So we can actually position A in the first place, B in the second place, because once the A is placed in the first position, then you cannot place A in the second position, because each element only allowed to appear exactly once. So you have A, B, C. That's one case, right? And then that's one sequence. Okay. Now we can actually create another sequence. The first thing is A. Now the second one we can place C, B. Right? That's a second sequence. Okay, another sequence. And then we can put the B in here, A, C. We can put the B, C, A. And then we can put the C at the first place, and the A, B, or C, B, A. Is there any other sequences we just missed? And looks like that's pretty much all the sequences we're going to talk about. So for the S, there are a total of 6 different permutations. Okay. So now let's talk about this. Suppose in the encryption algorithm, we choose the S as a sequence of English alphabet, A, B, C, D, E, F, G, H, I, J, K, and all the way to X, Y, Z. Now in this case, the total number of elements is 26. Right here, it's 3. Now how many sequences we can actually create different sequences, or how many different permutations? So you can use A, B, C, X, Y, Z. That's one sequence, right? That's one permutation. Okay. Now there's so many of them. So let's forget about this. Let's first take a look at this question from another perspective. Let's say, so with 26, now each sequence is going to take 26 positions, right? for the first position, how many different letters we can put in there? We can definitely put an A in there. We can definitely put a B in there. C, D, or X, Y, Z, right? How many different letters we can, place in the first position? That's 26, right? Now, once we actually select an element or select a character, then in the first position, let's say we select X, then for the next position, how many letters we can select? Remember, you can select A, B, C, but we cannot select X because X is already selected. Okay, so that means we have total of 25 different letters to select. Now suppose we select B in here. So now for the position 3, how many letters we can select? 24, right? We can select any letters except X and B. So we keep that way. So the next one going to be 23, So now the more actually we select, then the less choices we have. Okay, so the last one is 1 because once everything else is selected, for the last position there's no other choice, only one, the leftover one. So this is 2, this is 3, Now how many total number of permutations we may have? The first one we have 26. Once it's selected, we can do 25, 24. What is this number? That's 26 factorial. Okay. Now, using our monoalphabetical, we can map the alphabet A, B, C, X, Y, Z to any of these permutation. Okay. So, how many different permutations we have? 26 factorial. So that means, each of the, in each case we can map to any one of these permutations. So how many different keys we may have? We have a total of 26 factorial number of keys. Okay. That's way more than the Caesar cipher, which has only 25 different keys. Okay, that's a huge number. So no monoalphabetical is definitely better than the Caesar cipher, but is the monoalphabetical cipher secure? Let's see. Okay, so before we talk about the monoalphabetical cipher, let's first introduce a term called permutation. Now, what is a permutation? Permutation of a finite set of elements S is an ordered sequence of all elements of S, with each element appearing exactly once. Now, let's take a look at the example. Suppose we define a set of elements S. Now, how many elements S contains? Let's say S contains A, B, and C. 3 elements. So in this case, N is 3. S contains 3 elements. Now let's see. We define one sequence for S. Okay, that's one permutation, right? So let's say A, B, C. That's one sequence of all the elements of S, because S contains all 3 elements, A, B, and C. So this sequence contains A, B, and C. Now also, if A appears in position 1, then A cannot be shown in the second position and the third position. So that means once A is selected in position A, then you cannot have A in the second position and the third position. So that's a reason why all the elements are distinct. Okay. Now let's take a look at another sequence, A, C, and B. this is definitely a different sequence. That's also a permutation, right? And then we can select some others, like a B, A, C, B, C, A, and then lastly we can put a C in the first position, A, B, and C, B, A. Are these all the permutations for 3 elements? Let's see. The answer is actually yes. So for S, which contains 3 elements, the total number of permutations is 6. Now how can we get this number? How do we know that 6 is the correct number? Let's take a look at this question in detail. Okay, suppose we're gonna actually create the sequence of elements of S. Okay, S has 3 elements, so we have 3 positions. 1, 2, 3. Now, for the first position, how many elements we can select? Okay, now the first position we can select A, right? We can put A in the first position, and also we can select a B or C. So basically, there are 3 different options. Okay. Now, once the first position is settled, so that means if we select B in the first position, then we will take a look at the next position. Since B is already selected, so now you can select A in the second position or C, not B, right? Why? Because based on the definition of permutation, then we can select the sequence of all the elements of S with each element appearing exactly once. Okay, so since B is selected in position 1, so you cannot select B in position 2. So in second position, you have 2 options. Okay, now let's say we selected C in second position, and then for the last position, position 3, how many different options we have? We don't have much of the option, right? The only element we can select is A. So there's only one option. Okay, so in the first position we have 3 options. Once the first position we select the element in the first position, then the second one we have 2 options. So we have a total of 3 times 2 times 1. That's 6. Okay. Now in math, if we have any kind of sequence like this, 3, 2, 1, then that's the factorial, right? 3 factorial. So this is actually generally true. So for 3 elements, we have 6, permutations. Now, if for the S with general n elements, then we have n factorial, which is n times n minus 1 times n minus 2, and times 3, 2, 1, right? So that's the n factorial. Okay, now let's go back to the monoalphabetical cipher. Suppose the set of elements S contains A, B, C, and all the alphabet in English language, X, Y, Z. So in this case, n equals 26, right? So that's a total number of elements in the English alphabet. So then with S, we can create 26 factorial permutations. Now, 26 is a huge number. If we calculate, 26 is approximately 2 times 10 to the 26 possible permutations. Now, if we map the original sequence A, B, C, D all the way to x, y, z. We map A to any element in the S. A could map to A, it could map to B. So you have 26 choices. B can map to the remaining 25 different elements, right? So then that's the total number of 26 factorial different keys. So 26 factorial possible keys. That's a huge number. Okay. So is the monoalphabetical cipher safe? Definitely it's safer than the Caesar cipher, because Caesar cipher has only 25 keys, but now we have 26 factorial number of keys. But it's really safe. You know, it's safer than Caesar cipher, but it's still safe. We'll see. We'll talk about these things later. Okay. So let's take a look at the first question. Is monoalphabetic cipher secure? Now let's take a look at the brute force attack. Suppose I use the brute force attack. Okay. So if I actually try to perform the attack, remember there are the total number of keys for the mono cipher, you know, is 4 times 10 to the 26. That's the total number of keys. Okay. Now if I use the brute force attack with a computer, right? Suppose I have a very powerful computer. The computer can, you know, try. The computer can try 1 billion keys per second. Okay, try 1 billion. 1 billion is 10 to the 10. Now in each second I can try 1 billion keys. Okay, so now let's see how many keys I can try in 1 minute. Okay, so in 1 minute, that's 1 billion a second times 60, right? Because 1 minute is 60 seconds. So 10 to the 10 times 60. Okay, that's the number of keys I can try using brute force attack in a minute. Now, what about an hour? Okay, 1 hour is 60 minutes. So I multiply by 60. You know, that's the total number of tries I can do with 1 hour. I can do the similar things for 1 day because there's 24 hours per day. So that's the total number of keys I can try in a day using mono alphabetical. What about a year? A year is 360 days, right? If I multiply by 360, that's the total number of keys I can try in a year. Now, what is this number? Let's see. I did the math. So I find out this is about 3.11 times 10 to the 17th. So that's the total number of keys I can try in a year using my computer, which can process 1 billion keys in a second. So in 1 year, I can try these number of keys. Now, what does that mean? Okay, so that's the total number of keys I can try in a year. So now with total of 4 times 10 to the 26 keys, how many years do I need? I can do another math. So that's the 4 times 10 to the 26 divided by 3.11 10 to the 17. So that's the number of keys I can try in a year. That's the total number of keys divided by the number of keys I can try in 1 year That's the total number of years, right? What's the number? The number is about 1.2 times 10 to the 9. Okay, so that's the total number of years I need to have. Let's forget about 1.2. Just take a look at the 10 to the 9. What's that number? That's 100 million years. So now, if I use a powerful machine which can, basically try 1 billion keys per second, okay, using brute force attack, and I continue to do that, and once I finish all the keys using brute force attack, which is 4 times 10 to the 26, then I need more than 10 or 100 million years. Okay, what this is called. Okay, so technically it's impossible, right? Because that's too long. That's ridiculous. Now, so that means with brute force attack, the monoalphabetic cipher is secure. Okay, I'm saying it is secure with respect to the brute force attack. Okay, so that's also called computationally secure because the time spent on cracking the keys is unacceptable. It's more than 100 millions. Okay, that's actually much longer than the entire human history. Okay, so monoalphabetic cipher is secure with respect to the brute force attack, but is it really secure? Because when we try to crack any algorithm, we can use any cryptanalysis ways. Brute force is one of these. Okay. Then let's take a look. Someone actually, a smart people, figured out a way to crack these monoalphabetic cipher. What the way they use is called attack using the frequency of the alphabets. Using the frequency of the alphabets. Now, if you pick any book, any textbook, any kind of book like encyclopedia or any you pick any book with English languages. Okay. Now we can, if the book contains like 500 pages or 1,000 pages, whatever the number of pages. Now you can count the frequencies of each English characters. Okay. You count the frequency of A, you count the frequency of B, C, D, E, and then you will find out the frequency of each letter is very stable. Now, if we actually check the frequencies of a book with more and more and more paragraphs, sentences, then that number is very stable. Okay. Now it says 8.167% of the time, you can see the letter A. So the letter A will appear a little bit more than 8% of the time. Okay. The letter with the highest frequency is, what is that? Is E, which is more than 12%. Now some of the letters are, has a very low frequency, like a J, Q, X, Z. Okay. Now T has a very high frequency, which is about 9. Then the other one, O, L, E is definitely the highest. Now, how can we use this frequency of the alphabet to crack these monoalphabetic cipher? Let's take a look. So let's take a look at the following ciphertext. Okay, So the first letter is U, Z, Q. That's a ciphertext. Since we cannot use the brute force attack, remember the brute force attack is not realistic, but it's not a Caesar cipher. So because every letter shifted a different number of positions, right? So we cannot use the brute force attack because it's not a Caesar cipher. Now, can we use the frequency of alphabets to analyze it? Okay, let's see. Okay, so now let's apply the frequency of characters to figure out what could be the original plain text. Okay, hopefully we can solve that problem. Let's see. Here's the ciphertext we just mentioned. Okay, I counted the total number of characters. It is 120. Okay, and then here we calculate the frequency of each character. Okay, and we line up based on the number. So P has the highest frequency, and looks like R, N, these has the frequency 0, which means it never appear in the ciphertext. Okay, now let's take a look at the example of P, and to figure out how can we calculate the frequencies. Okay, so the first thing we need to do is we need to count the number of P's in these ciphertext. Let's see. We have a P here, 1, 2, 3, 4, 5. So it looks like we have 5 P's in the first line. And then 6, 7, 8, 9, 10. Okay, so we also have 5 P's in the second line. And then 11, 12, 13, 14, 15, 16. Do we have any more P's? Looks like no, we have 6 P's. So we have a total of 5 plus 5 plus 6. We have a total of 16 P's. Now, to calculate the frequencies, we need to divide the number of P's, which is 16, by the total number of characters, right? That gives you the frequencies for that particular character P. And when we calculate it, we will get 13.33. And we will do the similar things for Z. We counted the number of Z's in this ciphertext and divide the number of Z's by 120. And so we calculate each of these. Now what's the next step? The next step is we need to compare the frequencies in that list and with the relative frequencies in that in the diagram. Now we find out P is 13.33, which is highest. So most likely we're gonna assume that the letter P is mapped from E, right? Okay, so P is from E. Now what about the Z? Z is 11.67. Now looks like the second one in the frequency diagram is T, right? It's a 9%. Okay, and A is also close. It's a 8.167%, and maybe O. Okay, so we have to try each of this and compare with the use the knowledge of English language. The more we map, the easier we can figure it out. And let's say the Z actually was mapped from the English letter T, and we had tried this map. But then, if this map doesn't work out, we can try the other thing. We can assume that probably it's coming from A. C is mapped from A, right? So that's the way we're gonna do the analysis. It's not an easy one, but it's not impossible. Okay, because mostly in the English language, once we can actually figure out the couple of high frequency letters, we can fill the puzzle, to fill out the remaining letters. Okay, that's a kind of interesting game we can play. Okay, so now let's actually look at the mapping, right? So we know P has the highest frequency. We assume that P was originally mapped from English letter E. And we also try the Z. We initially believed that Z was mapped from T. Now we will try to fill the T in the position of Z to see whether this makes sense. So initially we actually only mapped 4 letters. Okay, 4 letters has been identified. But if you look at the whole thing, because these are the 4 which have the highest frequencies. So already we have quite a bit of messages. Okay, now we continue these analysis of frequencies. Now also plus the try and error, we should eventually yield a solution from this point. Okay, so here, for example, we already identify a word, right? And here is another word. Okay, and here we have th, and then we can figure out, is there any actual word starting with th and ending with this? We can guess it. Okay, so that's basically the idea of the frequency of characters. So we're not going to actually spend much time on this, but eventually the final answer for this is, this is the original message. Okay. Still not easy, but at least, with the help of the frequency of the characters and with the help of some of the expertise in the language, English language, we can pretty much fill out the puzzle and eventually solve this puzzle, right? Okay, so as we have seen in the previous slide, you can use the frequency to, guess who was the original letter, right? So basically, mono alphabetical cipher is easy to break because they reflect the frequency data of the original alphabet. Because with the same original letter, it will map to the same, cipher text letter. So that's the problem with the mono alphabetic cipher. Even though you have so many keys, then the brute force attack is kind of impossible. But you use the frequency, then you can still figure out, the original one. And also, the countermeasure is to provide a multiple substitutes for single letters. Because once we actually fill more positions, then we can actually use the diagram or trigram. The diagram is basically 2 letter combinations. For example, if we frequently see 2 letters combination, and then we can pretty much use the frequency of th, the diagram, to guess this. So basically, and the most frequently used word is like the, the trigram. So if in the ciphertext, the any actually sequence of 3 characters appear multiple times, and which match the frequency of the the, then we can actually, pretty much guess, okay, these 3 probably going to be the the. Okay, so with the help of frequency and the help of the frequencies of the diagram or the trigram, so mono alphabetic cipher is not difficult to crack, Okay, so that's the end of module 2A. Thank you.